The infinite square well is the first toy model that we can apply what we know about quantum mechanics. It's defined by two barriers, one of them being at some point, so let's say x equals 0, and another one defined at, let's say, point x equals a, and they go off into infinity. So what this means, and then everything in between is potential equals 0. So what this means is that the particle cannot exist out here or out here because the particle can't have infinity potential energy out here. But in the middle, it can have 0 potential energy, which means that it has equal probability of existing anywhere within the infinite square well, so between 0 and a. So when we apply this to the Schrodinger equation with a potential is equal to 0, the only place that the particle can exist, we have a relatively simple differential equation to solve. And whenever you do solve it, you get point number 1. There are multiple solutions to this, and they can all be represented by these terms here. And again, this is the spatial component here, and this is the time component here. So all these different solutions just require them to have, in the middle, have some sort of valid function, but they all, as long as they meet to 0 out here, as long as they terminate, they don't exist, the probability goes to 0 by the time it gets to the potential square, the barriers. So they can look like this, it can look like this, kind of, it can look like that, as long as they terminate to here. So so you can have something kind of crazy as long as it's a valid wave function, and it's going to be a solution to the differential equation. So that's why you have your psi sub n, is that there's essentially an infinite amount of solutions, but they're all going to generally look like this with different n's. And by the way, that E sub n for the energy, each one's going to have different energies, and they are always going to be 1 over 2m times pi n h bar over a squared. So these are all your different types of what's called stationary states, the solutions to the Schrodinger equation, as long as you have these boundary conditions. Now, if you have a specific wave function that exists in the infinite square well, say something like that, of course it'd be more straight, but anyways, that can be represented as a linear combination of a bunch of different stationary states, right? And eventually, once you add them up with different varying amounts of representations, which is the constants that you multiply them out in front, you'll eventually get something like looking like that. It's something that we did in classical mechanics for standing waves, and that's where you arrive at point 2. Any valid wave function can be represented as a linear combination of stationary states as long as they're weighted differently or weighted appropriately, right? So this one might be weighted a little bit more than this one perhaps and stuff. And so you can make essentially anything out of these stationary states as long as you have the right constant out front, the modulus out in front, that kind of weighs how much of them are represented in that wave function. Now, that weight for each stationary state is kind of important, and so you want to usually solve for that. So you can use what's called Fourier's trick to solve for those different modulus out in front, those weights. And as long as you have all these informations here, then you can solve for that constant out in front. And again, it's time equals 0 here because the time dependence doesn't really matter whenever you're looking at the modulus squared for each one, and that's something we covered in the previous chapter. Now, once you have that modulus out in front, you can use that to find expectation values, such as point number 4 here. So the expectation value of the Hamiltonian, which is like the average energy for the entire wave function for every linear combination of stationary states that's used to represent that wave function. That's relatively easy to find as long as it's not like an infinite linear combination. You just find the magnitude squared of each state that's represented by the wave function, and you weight those, or you basically weight each energy that's represented in the wave function by the modulus squared. And the modulus squared is essentially the probability of finding that energy state that exists in here. So the average is just basically the weighted sum of all the energies that are represented in that wave function. But if you wanted to find the probability of finding it in state E sub n, or having it energy E sub n, then you would just find the modulus squared of that corresponding energy state. So for example, if you wanted energy state 2, if you want to find the probability of measuring energy state 2, then you would just take the modulus squared of the state 2. And again, of note, the expectation value isn't always a possible measurement of the energies. It's just the average. For example, if you like roll the dice and 6 face dice and you rolled it as many times, you took the average, you would get 3.5. But that's not an average. That's not an actual value on a dice. It's just the average that you would actually get. So if you get something wacky, seemingly wacky for the expectation value of the Hamiltonian, like it's not a possible measurable energy, that's fine. It's just the average.